We want to spend some time talking about the different properties of functions. But before we get into that, we need to answer the more basic question of what is a function? There are different ways to go about defining this, but one relatively simple way is to say that a function is a relation where every input has one unique output. Or another way of saying that is every x value is paired with a single unique y value. If we look at the example that we have in example 1, we're given a relation, which is a series of 4 coordinate points, so xy pairs, and the question is if this relation is a function. What we need to investigate are each of the x values to first see if any x values are repeated. In this case, no x values are repeated, so we know we have a function because no x value can be paired with a different y value. So in this case, yes, we do have a function. And if we do have a function, then we can start talking about the domain and range of that function. When we talk about domain, we want to identify all possible x values that exist for that function. Since in this case we're just dealing with 4 discrete points, our domain is simply the x coordinates for each of those pairs. So 6, 7, 8, and 9. Our range is a list or a statement containing all possible y values for our function. So what we'll do is identify all of our possible y values, which in this case is 4, 4, 4, and 4. But we don't need to list those different values repeatedly, so we'll simply state that the range is just 4. One thing to make sure you're catching on to here is that even though we have these repeated y values, that doesn't prevent our relation from being a function. It's okay if our y values are repeated. What we're concerned about is a repeated x value paired with 2 different y values. If we look at example 2, we'll see that we have 2 points that both have the same x coordinate, 8 and 8. The first time that 8 occurs, it's paired with a 4. The second time it's paired with an 18, meaning that input does not have a single unique output, so no, this is not a function. Because that output for 8 is not unique. So we still have a relation in example 2, but that relation doesn't meet the conditions for being a function. We can take this same idea and consider it while looking at the graphs of functions. In example 3, we want to investigate if this graph is the graph of a function. One way to investigate that is to apply what we refer to as the vertical line test, which is simply a process of drawing vertical lines over and over again through our graph and making sure that anywhere we would draw that vertical line, we would only intersect our graph in one place. Which is again really just reinforcing that idea of every x value only is paired only with a single unique y value. So in this case, yes, we do have a function because it passes the vertical line test. Every time we have an x value, it's only paired with a single y value, which means we can also establish the domain and range of this function. Instead of having a list of points, now we have a continuous smooth curve. So our domain and range are going to have an infinite set of points. Rather than list those individual values, which would take forever, we'll use interval notation to represent those infinite intervals of numbers. When we look at domain, again, we're talking about all x values for our function, all x values that would be included in our function. Even though they're not expressed on here, we can add little arrows onto either end of this graph to suggest that this graph is going to continue increasing in both directions, meaning no matter how far we move along in the x-axis in the positive direction or in the negative direction, we would still be able to work our way up and intersect that graph. So that tells us that our domain in this case is going to be negative infinity to infinity, meaning all real numbers are included in the domain. When we talk about range, though, we're going to have a restriction. Since our graph continues increasing in that vertical direction, our y variable won't have an upper bound, but as we move in the negative direction for y, we hit y equals -4, and then our graph doesn't exist anywhere below that. So our smallest possible y value is -4, and then we can have values larger. So our range could be expressed as the interval -4 with that square bracket, since -4 is included as part of the range, to infinity. In example 4, we're given another graph to consider. We can apply the vertical line test again. And with the vertical line test, we only need to find a single point or a single x value where we fail that definition for being a function. So in this case, this graph is not a function because our value of x equals 2 is paired with two y values. Which again, graphically we can identify by seeing that if we consider x equals 2, we have a positive y value and a negative y value associated with that x value. Again, if we can find a single x value where our function or where our graph fails the vertical line test, then the graph we're looking at is not the graph of a function.